into mechanical energy, which we can use to drive pumps, fans, compressors, gears, pulleys, etc. Almost all the parts are held inside the main housing. At the front, we find the shaft. This is the part that rotates, and we can connect things like pumps, gears, and pulleys to this to do work for us. At the back, we find the fan and a protective cover. The fan is connected to the shaft, and so it rotates whenever the motor operates. That's because the induction motor can produce a lot of heat when in operation, so the fan blows ambient air over the casing to cool it down. If the induction motor became too hot, the insulation of the internal electrical coils will melt. This will cause a short circuit and the motor will destroy itself. The fins on the side of the enclosure help to increase the surface area, and that lets us remove more unwanted heat. The shaft is supported by some bearings, which sit inside the front as well as the rear shields. The bearings help the shaft rotate smoothly and also hold it in position. Inside the housing, we find the stator. The stator is stationary and does not rotate. This consists of a number of copper wires which are wrapped into coils between the slots positioned around the inner perimeter. The copper wires are coated with a special enamel, which electrically insulates the wires from each other. This means the electricity has to flow through the entire coil. Otherwise, it would take the shortest path possible, and we'll see why that's important a little later in this video. Now, this is a 3-phase induction motor. So we have 3 separated sets of coils in the stator. The ends of each set will connect with the terminals within the electrical terminal box. We will also see how these are connected a little later in this video. When connected to the electrical supply, the stator generates a rotating electromagnetic field. Connected to the shaft is the rotor. In this case, it's a squirrel cage type rotor. It's called a squirrel cage because it has 2 end rings which are connected by some bars, and these will all rotate together. This design is similar to a small cage or an exercise wheel used by a pet hamster or even a squirrel. The squirrel cage is fitted with a number of laminated steel sheets. These sheets will help concentrate the magnetic field into the bars. Sheets are used instead of a solid piece of metal, as this improves the efficiency by reducing the size of the eddy currents in the rotor. When the rotor is placed inside the stator, and the stator is connected to an electrical power supply, the rotor will begin to rotate. So, how does this work? When electricity passes through a wire, an electromagnetic field is generated around the wire. We can see this by placing some compasses around the wire. The compasses will rotate to align with this magnetic field. If the direction of current is reversed, the magnetic field also reverses, and so the compasses will change direction. The magnetic field of the wire is pulling and pushing the compass dials. Just like if we slide 2 bar magnets towards each other, they will either be attracted or repelled. We can even use one magnet to rotate another. Or we could also rotate the magnet by changing the intensity of the magnetic field around it. If we place a wire in a magnetic field and pass a current through it, the magnetic field of the wire will interact with the permanent magnet's magnetic field, and the wire will therefore experience a force. This force will move the wire either upwards or downwards, depending on the direction of current and the polarity of the magnetic fields. If we wrap the wire into a coil, the electromagnetic field becomes stronger. The coil will produce a north and south pole, just like a permanent magnet. We call these coils of wire an inductor. When we pass an alternating current through the wire, the electrons will be constantly changing direction between flowing forwards and backwards. So, the magnetic field will also expand and collapse, and the polarity reverses each time. When we place another separated coil in close proximity and complete the circuit, the electromagnetic field will induce a current in the second coil. We can connect two coils together and place them opposite each other to create a larger magnetic field. If we placed a closed loop of wire inside this large magnetic field, we will induce a current in the loop. As we know, when we pass a current through a wire, it generates a magnetic field. And we also know the magnetic fields will push or pull each other when they interact. So, this loop of wire will also generate a magnetic field, and this will interact with the larger magnetic field. Each side of the coil will experience opposing forces, which causes it to rotate. This loop is therefore our rotor, and the coils are therefore our stator. The rotor will only rotate until it aligns with the stator coils. At this point, it will likely get stuck, as the induced current reverses with the coil. To overcome this, we need to introduce another set of coils in the stator, and we must connect these to another phase. The electrons flow in this phase at a slightly different time. So, the electromagnetic field will also therefore change in strength as well as polarity at a slightly different time. This will force the rotor to rotate. Inside the induction motor, we have three separated coils which are used to produce a rotational electromagnetic field. When we pass an alternating current through each coil, the coils will produce an electromagnetic field which changes in intensity as well as polarity as the electrons change direction. But if we were to connect each coil to a different phase, then the electrons in each coil will change direction at a different time. This means the polarity and intensity of the magnetic field will also occur at a different time. To distribute this magnetic field, we need to rotate the coil sets 120 degrees from the previous phase. We then combine these into the stator. The magnetic field varies in strength and polarity between the coils, which combine to produce the effect of a rotating magnetic field. We saw earlier in this video that current can be induced into a second coil when in close proximity. The bars of the squirrel cage are shorted at each end, which therefore creates multiple loops or coils. Each bar therefore induces a current and creates a magnetic field. The magnetic field of the rotor bars interacts with the magnetic field of the stator. The rotor bar's magnetic field is attracted to the magnetic field of the stator. As the magnetic field is rotating, the rotor will therefore also rotate in the same direction as the magnetic field to try and align with it, but it will never be able to fully catch up. The bars of the rotor are often skewed. This helps distribute the magnetic field across multiple bars and stops the motor being able to align and jam. The stator contains all of the coils or windings used to create the rotating electromagnetic field when electricity is passed through the wires. To power the coils, we find an electrical terminal box on the top, or sometimes on the side. Inside this box, we have 6 electrical terminals. Each terminal has a corresponding letter and number. We have U1, V1 and W1, then W2, U2 and V2. We have our phase 1 coil connected to the 2 U terminals, then the phase 2 coils which are connected to the 2 V terminals, and lastly the phase 3 coil which is connected to the 2 W terminals. Notice that the electrical terminals are arranged in a different configuration on one side to the other. We will see why that is in just a moment. We now bring in our 3-phase power supply and connect these to their respective terminals. For the motor to run, we need to complete the circuit, and there are 2 ways to do this. The first way is the delta configuration. For this, we connect across the terminals U1 to W2, V1 to U2, and W1 to V2. This will give us our delta configuration. Now, when we provide AC current through the phases, we see that electricity flows from one phase to another as the direction of AC power reverses in each phase at a different time. That is why we have the terminals in different arrangements in the terminal box, because we can easily connect across and allow electricity to flow between the phases as the electrons reverse at different times. The other way we can connect the terminals is to use the star or Y configuration. In this method, we connect between W2, U2, and V2 on only one side. This will give us our star or Y equivalent connection. Now, when we pass electricity through the phases, we see the electrons are shared between the terminals of the phases, due to their. Let's have a look at the difference between the star and delta configurations. Let's say we have the motor connected in delta, with a supply voltage of 400 volts. That means when we use a multimeter to measure the voltage between any two phases, we will get a reading of 400 volts. We call this our line-to-line voltage. Now, if we measure across the two ends of a coil, we again see the line-to-line voltage of 400 volts. Let's say each coil has a resistance, or impedance as this is alternating current, of 20 ohms. That means we will get a current reading on the coil of 20 amps. We can calculate that from 400 volts divided by 20 ohms, which is 20 amps. But the current in the line will be different. It will be 34.6 amps. We get that from 20 amps multiplied by the square root of 3, which is 34.6 amps. That's because each phase is connected to two coils. Now, if we look at the star or Y configuration, we again have a line-to-line voltage of 400 volts. We see that if we measure between any two phases. But with the star configuration, all our coils are connected together and meet at the star point or neutral point. It's from this point that we can run a neutral wire if needed. So this time, when we measure the voltage across the ends of any coil, we get a lower voltage of 230 volts. That's because the phase isn't directly connected to two coils, like in the delta configuration. One end of the coil is connected to a phase, but the other is connected to a shared point. So the voltage is therefore shared. The voltage is less as one phase is always in reverse. We can calculate this by 400 volts divided by the square root of 3, which is 230 volts. As the voltage is less, the current will be 2. If this coil also has an impedance of 20 ohms, then 230 volts divided by 20 amps equals 11.5 amps. The line current will also therefore be the same at 11.5 amps. So we can see from the delta configuration, the coil is exposed to the full 400 volts between two phases, but the star configuration is only exposed to 230 volts between the phase and the neutral point. So the star uses less voltage and less current compared to the delta version. Okay, that's it for this video, but to continue learning about electrical engineering, check out one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Instagram, LinkedIn, as well as theengineeringmindset.com.